When you picture a computer crashing, you usually think of like a melted ship, right?
Oh, yeah. Or, a wire snapping on a motherboard somewhere.
Exactly. We have this deep-seated expectation that system failures are purely physical. But today, we're looking at a completely different kind of failure. We're doing a deep dive into this landscape where a plane's flight controls or a computer's memory bank doesn't fail because of hardware, but actually because of a mathematical traffic jam.
Right. It's the absolute definition of invisible infrastructure. The math dictating the system can either be this superhighway that processes data flawlessly, or it can just be a brick wall that overloads the processor completely.
And navigating that highway is exactly what we are getting into today for you. Welcome to the deep dive. We are looking at a pivotal moment, a bridge where we cross over from pure abstract analytical math into applied real-world computational logic.
It's a really fun transition to make, honestly.
It really is. We are pulling from the notes titled Day 23 Definite Integral Symmetry, Theory, Domains, and Code. And our mission today is to explore how a specific mathematical shortcut prevents your systems from crashing, keeps airplanes flying level, and honestly, stops your electronics from frying.
Which is something we all take for granted.
Oh, 100%. But here's where it gets really interesting. This isn't about memorizing calculus. It's an exploration of the hidden structural laws that make our physical and digital universes operate smoothly, specifically looking at definite integral symmetry and substitution domains.
Yeah, to understand how engineers build these failure-proof systems, we kind of have to look at the primary tool they use, and that's the definite integral. It's how they calculate accumulated value over a physical space or time.
Right, which most of us remember, at least vaguely, from high school calculus.
Exactly, finding the area under a curve between two rigid boundaries. But in advanced engineering, the functions inside those boundaries are usually just way too complex to calculate directly, which forces engineers to use a technique called substitution.
Right, so you swap out the complex variable for a simpler one just to, clean up the workspace.
Exactly. You change it to make it manageable.
But there is a very strict rule when you do this, known as substitution tracks for definite bounds. If you swap the variable, say, replacing your x terms with a new u term, you absolutely must translate the physical boundaries of your system to match this new mathematical domain.
You have to. You can't just change the internal logic and keep the external borders the same.
That makes sense.
Yeah, if your original system was calculating a force from boundary A to boundary B using x, and you substitute x with a function of u, your boundaries strictly become a function of A and a function of B.
I always think about it, it's exactly like changing currency when you travel.
Oh, that's a good way to look at it.
Right. Like if you fly from New York to Paris, your original boundaries operate in dollars. But the math of buying things in dollars over there is too complex, so you do a substitution. You swap dollars for euros.
Right.
But once you do that, you don't calculate a price in euros, mentally convert it back to dollars, hand the barista dollars, and expect it to work. You just operate entirely within the new currency limits.
That is a perfect analogy. And what's fascinating here is how that principle dictates computational efficiency.
How so?
Well, the whole point of substitution in an algorithm is to save processing time, right? Converting the variable back to its original state at the end of the calculation entirely defeats the purpose. It just wastes memory.
Ah, I see.
You never have to convert u back to x. You just evaluate the new integral using the new translated limits.
Right. But I mean, as efficient as domain substitution is, the processor is still doing the heavy lifting of calculating that accumulated value point by point, right?
It is. It's still doing the work.
Which brings us to a way to bypass the heavy calculation entirely, like the ultimate algorithmic shortcut, the symmetry rule.
Yes. This is arguably the most powerful property of definite integrals. It comes into play when your boundaries are perfectly symmetric across the center of a graph.
Like integrating from negative a to positive a.
Exactly.
Yeah.
Rather than crunching the numbers from left to right, the engineer or the algorithm stops and inspects the internal structural parity of the function.
So it's looking at whether the function is inherently even or odd.
Precisely.
And we know the mathematical definitions of those. Like even functions mirror perfectly across the axis, like a standard parabola.
Right. Both sides go up.
Yeah.
No.
While odd functions are these rotational inversions, where the left side is the exact negative of the right side, like a sine wave.
But knowing those definitions is one thing. Visualizing the dynamic boundaries is what really makes this actionable.
Yeah, the source material actually talks about this interactive concept explorer built for these models.
I love that tool.
It's so cool. You can dynamically scrub the boundaries on a screen from -a to +a and just watch how the structural parity behaves under integration.
Right, so if you think about it, as you slide those boundaries wider on an odd function, you see a negative area stretching down on the left and a positive area stretching up on the right.
And because integration is net accumulation, no matter how wide you drag those boundaries, the net total stays locked at exactly 0.
Exactly. The positive and negative perfectly mathematically oppose each other. They just zero out.
But switch to an even function and the areas compound.
Right. They build on each other symmetrically.
And that visual understanding is the key, isn't it? Because out in the real world, recognizing whether a physical system is behaving like an even function or an odd function completely dictates your computational approach.
It changes everything. If it's even, you just integrate from the center to one side and multiply by 2. If it's odd, the result is just 0. You don't even have to do the math.
That physical cancellation is so intuitive when we talk about abstract graphs. But how does that translate to actual metal and software?
Well, let's take aerospace engineering. An aircraft in flight is basically a massive exercise in managing symmetric boundaries. Think about the aerodynamic loading on a perfectly symmetric delta wing.
Okay, so we're measuring the fluid dynamics from the far left wingtip, which is our negative boundary, across the fuselage to the far right wingtip, which is +a.
Right. And if that aircraft is in steady, level flight, the wind hitting both wings is equal. The lift distribution across that wingspan is an inherently even function.
Okay, so if you are an aerodynamicist running a fluid simulation like a Navier-Stokes simulation, which, takes immense computational power because it's calculating millions of finite elements in a mesh, you don't simulate the wind over the entire aircraft.
No, you would waste days of supercomputer time doing that. You only calculate the integral from the fuselage centerline, which is 0, out to the right wingtip, which is +a.
And then you just apply the symmetry rule and double the result.
Exactly. You cut the computational workload exactly in half without losing a fraction of a percent of accuracy.
That's wild. But planes maneuver, and this is where we introduce the odd function, right?
Right.
Because to roll the aircraft, a pilot uses ailerons on the trailing edges of the wings. The deflection pushes one wing down and pushes the opposing wing up.
Right. So one side is the exact negative inverse of the other.
Which turns the aerodynamic load across the wingspan into a pure odd function.
It does.
Okay, let's unpack this. If an aileron roll introduces a pure odd function, and odd functions from -a to +a equal exactly 0, why doesn't the plane just drop out of the sky when you roll?
Because you're generating a net zero change in vertical lift, right?
Yeah, that's what I mean.
Well, net zero change doesn't mean 0 total lift.
Yeah.
The baseline lift, keeping that plane up in the air, is a massive even function across the entire wingspan.
Ah, I see.
The roll maneuver just introduces a secondary, highly localized odd function on top of that baseline.
Okay, so the baseline keeps you at altitude, while the secondary odd function generates a differential torque around the aircraft's longitudinal axis.
Exactly. And the crucial takeaway for the fluid dynamics algorithm is that it doesn't have to recalculate the entire lift coefficient for the whole plane during a roll.
Because the odd function zeroes itself out in terms of vertical translation.
Right, allowing the computer to focus purely on the rotational moment.
The math isolates the physics. That's incredible. But, that physical cancellation is somewhat intuitive because we can literally watch a plane twist in the air. Let's look at how this same mathematical cancellation happens invisibly in our walls.
Oh, this is a great example.
Right, because it's literally the reason your laptop isn't melting right now.
Yeah, we're talking about electronics and signal processing. Specifically, alternating current integration and DC bias.
The electricity coming out of a standard wall outlet travels in a pure sine wave, right? Which is fundamentally an odd function.
Yes, it peaks at a positive voltage, crosses 0, and dips into an identical negative voltage.
So if an electrical engineer integrates that pure AC wave over a full symmetric cycle from negative time to positive time, the result is 0. The positive voltage is perfectly canceled by the negative voltage.
Mathematically, yes. But obviously, the appliances plugged into your wall use power. The energy is doing work.
Right, my laptop is definitely charging.
Exactly. And this is where the engineering reality forces a shift in the mathematical identity of the system. Measuring voltage is different than measuring power dissipation.
Okay, because to calculate the power turning into heat through a resistor in, like, your laptop charger, we use a specific formula.
Right. Power equals voltage squared divided by resistance.
And we really have to ask why the physical formula squares the voltage.
It's definitely not an arbitrary mathematical trick. Power is the product of voltage and current. And in a simple resistive circuit, the current moves in exact lockstep with the voltage.
So when the voltage reverses direction into the negative, the current also reverses direction into the negative.
Right. And physically, the electrons are still colliding with the atomic lattice of the resistor. They are generating friction and heat regardless of which way they flow down the wire.
So mathematically, a negative voltage multiplied by a negative current yields a positive power output.
Exactly. Squaring that odd sine wave forces the structural parity to flip. It becomes an even function.
Oh, wow. So the negative dip of the wave folds upward, becoming a positive mirror image.
Yes. The structural parity flips completely. The energy strictly accumulates, just like that blue area compounding in the interactive visualizer we talked about.
And because plugging in a resistor changes the system from odd to even, the electrical engineer now applies the even shortcut.
Right. They only calculate the power dissipation for half the cycle, from 0 to the positive peak, and multiply it by 2.
That is so elegant, and rewriting the mathematical identity via physical components leads us directly into our final domain, doesn't it?
It does. Rewriting software rules.
Right, because everything we've discussed so far, aerospace, meshing, thermodynamics and circuits, it all relies on algorithms, and those algorithms need to be optimized.
Oh, absolutely.
This is where theoretical math directly prevents server farms from crashing due to data overload. We're talking about big O notation, computational complexity.
Yeah, and you have to remember, a central processing unit is not inherently intelligent. It is just relentless.
Right.
If a system feeds a CPU 10 million data points representing an odd function across symmetric boundaries, the CPU will default to brute force. It will dutifully crunch every single floating point decimal, iterating 10 million times, only to arrive at a final answer of 0.
Which is just a huge waste. In computer science, an operation that scales linearly with the amount of data is an O of n workload. 10 million points take 10 million processing cycles.
And if you have 100 million points, it takes 10 times longer. It's an immense bottleneck for the system.
But if the software architect understands definite integral symmetry, they don't let the CPU reach the data in the first place.
No, they build a mathematical culling mechanism directly into the code.
And the Python code implementation from the notes is beautifully simple. It's essentially a single conditional check. If Antor's underscore odd function returns 0.
That logic completely bypasses the O of n workload. It drops down to O of 1, which is constant time execution.
So it doesn't matter if there are 10 data points or 10 billion, the result is returned instantly.
Instantly.
But, I mean, how does the code actually know? How does an algorithm look at a complex mathematical string and determine its structural parity on the fly before it does the math?
Well, the Python script relies on a calculation engine that builds an abstract syntax tree.
Okay.
It parses the mathematical expression by breaking it down into nodes. So it looks at the structure, it sees a sine node, it flags it as odd, it sees an exponent of 2, it flags it as even.
Oh, right.
It refers to this tree, applying parity rules at each junction. If the top-level node resolves to an odd parity and it verifies the boundaries are symmetric, it triggers the culling.
I think of it like a bouncer at a massive club.
Okay, I like that.
Right. So the brute force O of n method is the bouncer checking the ID and running a background check on every single one of the 10,000 people in line.
Which takes forever.
Exactly. But the O of one algorithmic bouncer just looks at the line, sees a rule that says nobody wearing a red shirt gets in, and instantly turns away the entire crowd wearing red without checking a single ID. The resolution is immediate.
That is exactly what's happening. And this exact culling technique is the backbone of real-time physics engines in video games and simulations.
Yeah, let's visualize a massive explosion in a physics engine. A building collapses and you have thousands of pieces of digital debris, smoke particles, and shock waves interacting all at once.
Right, the engine has to calculate the trajectory and collision vectors of every single fragment 60 times a second to maintain the frame rate.
And if the engine evaluates every opposing vector manually, the simulation stutters, the memory buffer fills up, and the game crashes.
But the engine is programmed to seek out symmetry. If two explosive forces are acting symmetrically and oppositely on a piece of debris, the physics engine parses the vector math, recognizes an odd function over symmetric bounds, and returns a net force of 0 for that specific interaction.
It bypasses the calculation entirely.
Yes. It culls the invisible data. It saves that memory overhead for rendering the visible elements of the explosion.
It's literally teaching a machine to find the structural shortcuts that human mathematicians mapped out centuries ago.
And if we connect this to the bigger picture, elegant programming is no longer about trying to make silicon chips physically clock faster.
Right, because we are rapidly approaching the thermal and quantum limits of how fast physical hardware can process data.
Exactly. True software elegance today is about teaching algorithms the structural laws of mathematics so they can avoid calculating altogether.
Working smarter on a microscopic algorithmic level. I love it.
Me too.
Well, we covered a lot today. We started out looking at the rigid rules of substitution limits, understanding that when you swap domains, you have to map the physical boundaries to match.
Right.
Then we moved into the geometric reality of parity, seeing how even functions compound symmetrically while odd functions perfectly cancel out.
Such a powerful visual.
It really is. And we tracked how those abstract properties govern reality for you. We saw how aerospace fluid dynamics cuts supercomputer time in half, why the thermodynamics of an AC circuit flips a system from odd to even, and how real-time abstract syntax tree parsing drops massive linear workloads down to instantaneous O of one execution.
It's everywhere once you know to look for it.
It really is.
Yeah.
So what does this all mean for you? It means that the high-performance world around you is secretly held together by what the computers are not doing.
That's the secret.
The turbulence-free flight, the cool power brick on your floor, the flawless physics simulation on your screen, they all operate smoothly because the underlying math knows exactly when to step back and simply return a zero.
And this raises a really critical question to consider as you dive deeper into these concepts on your own.
Oh, definitely.
We currently design our most advanced infrastructure by heavily relying on the fact that physical forces and mathematical properties naturally cancel out. It is our ultimate computational cheat code.
Yeah.
But as we push toward creating infinitely complex digital universes and near-perfect quantum simulations, will our success rely on our ability to engineer raw computing power that can brute force every single variable?
That's the big question.
Or will the future of technology depend entirely on our mathematical ingenuity? Our ability to discover even deeper hidden mathematical zeros to cheat the workload before the processor ever even spins up.